it doesn't follow the sequence. So chapter 7 is actually parallel input output ports. It's one of the most easiest one, and definitely there's question on this on usually question number 3 in the final on the parallel input output port. And this is one of the very crucial one because you after this chapter, that means now you can. Do you know there's another video on Proteus, right? Yes. So watch that video and get that Proteus installed, because next week your mini project title is coming out. No, not next week, this week. So your mini project title is coming out. So you need to do that mini project. Is it okay? So watch that video on the Proteus. It is okay. So we're going to go to chapter 7 now. We go through some of the theoretical part first, and then we're going to go through some of the examples using Proteus, and we're going to see how to actually configure the info. So it's quite easy. So let us actually carry on. So embedded products, that means the PIC 18 that we're going to use, all those microcontrollers, whenever you program it to become an end product, usually the end product will be something more or less something like embedded products. Embedded products, we have seen the definition of embedded products in chapter 1, right? So embedded products are designed to allow the user to provide input to receive result. So a lot of electronic application allows us to actually enter the input, usually through button or usually through the touch screen or whatever. But embedded products or any embedded product allows have the interaction of input and also output. It receive some input and it displays an output, maybe in LED form or in the graphical form or maybe in terms of sound. So always there is an interaction between the input and also output. So the speed and characteristics of input-output devices are actually quite different from the CPU. One of the very simple basic input or output device, or let's focus on the input device, would be the switch. Now the characteristics of input-output devices, what do they mean by quite different from CPU is, CPU, the way how it processes is extremely fast. But when the input-output device is actually slow compared to the CPU. So there is an incompatibility between the speed of the CPU and also the input or the output speed. So because there is incompatibility, peripheral chips are actually used to resolve the difference between the input-output devices and also the CPU. Now if you open your motherboard, there's a lot of peripheral chips. Those peripheral chips is actually interfacing between the CPU and, let's say for example, the VGA, your USB, whatever. All those are actually outputs, right? Your VGA ports, your USB ports, all those are outputs. And all this are being controlled by the CPU, but the speed of the CPU is actually very fast. So whatever differences in terms of logic or in terms of speed is actually being taken care of by the peripheral, what we call them as the intermediate chips. They will actually take care and sort out things. So all these things is just for your knowledge. The major function of the interface chip is to synchronize. So this is the word. To synchronize the data transfer between the CPU and input-output devices. Because the CPU processes things too fast. It's not as, and the input-output ports are not as fast as CPU. So it needs to synchronize. So the peripheral device will actually synchronize the data received from the CPU and to be sent to the output port. So it will synchronize, it will make sure that the port is ready to actually transmit or the port is actually ready to receive. So this is being controlled by the interface chip. So resistors may be needed to limit the current flow, whereas buffer chips may be needed to increase the current flow required by the input-output devices. So for example, from the microcontroller, when we want to interface to LED, usually we'll use a resistor of 330 ohm because we want to limit the current. Of course, without the resistor, your LED will still turn on, maybe not for long. Turn on like lifespan might be reduced, so you want to reduce the current. And at the same time, sometimes you may need buffer chips. For example, your microcontroller, if you want to interface it with 7 segment. 7 segment is actually consists of a lot of LEDs inside it. But the thing is, it doesn't have enough of power to actually turn. Of course, the 7 segment will still turn on, but it will be very dim. So it will be very dim. So therefore, you need buffer chips. We have learned about buffer chips like 7.4, 7.5, 7404, I can't remember the series, but you have to use this chip in digital lab, right? 74 series. So those are actually buffer ICs. That means they are actually used to increase the current. So if you can actually drive 7 segments or motor which requires higher current, which the microcontroller cannot supply. So either you use resisting if the output devices requires less, you use resisting, or if the output devices require more, then you have to use buffer to amplify support. Is it okay? Are you following up to this point? KO. For example, this is actually a Proteus. Here, microcontroller is actually connected to the LED drive. It's actually you are required to actually put a resisting, current resisting resistor here. 330 ohm limit current going LED. So likewise.
Proteus.
Whenever this is 7 segment, of course here the 7 segment you see is without buffer IC. Take note that because this is a simulation, but in actual reality you need a buffer. You cannot connect straight like this. Can, but it will be very deep. It won't be so. You get the idea? Going back here. Any question up to this point?
Proteus.
An interface chip consists of control resistors. So just now we mentioned the interface chips actually synchronizers. So what are the components of interface chip? It usually consists of control registers, data register, status registers, data direction register, and control circuitry. These are part of the very general, what we say, interface chip will consist of all these components. Now, control registers allow the user to set up operation parameters. So these are some of the functions of those registers. So you can actually use them whether you want to do a read function or you want to use a write function. So you can actually use the control registers to control. Data registers hold the data to be output or received. This data register holds the value. Whenever there's an input, the input value will be held at the data registers. So at least you can read from the data registers. Status register records the status of the input operation. So this will keep track of what's happening. Data direction register allows the user to set the direction of the data transfer. So this one we'll see later. So each pin of the microcontroller is known as a digital input-output pin. Meaning to say that you can configure the pins to be input, you can also configure the pins to become output. So depend on how you configure. So how do you configure is by configuring this data direction register, which we will see later. To input, the processor reads the data from the data register. As I mentioned, whatever input that comes through from the input device is actually stored in the data register. So the CPU will read the data from the data register. Likewise, whenever you want to output, the processor writes the data to the data register. From the data register, it is pushed out to the output pin. So the interconnection between the CPU and also, so this is actually your CPU. So you have the interface chip. And whatever data is actually being sent to the interface, sorry, this is from input device. So remember inside the interface chip got few other registers, right? 5 registers inside. So it will store in the data register and the CPU will actually access it from here. Likewise, whenever we want to send the data out, it actually will send to interface and from here it will actually go out to the output device. Of course, why we have the address decoder is to select which port that we want to send it out to. So So the address decoder only allows one interface chip to exchange data with the microprocessor at a time. This one. So when it comes to input-output addressing, whenever we want to output or input, receive some input, we need to actually specify the input port or output ports, right? The address. So in this case, we don't have to worry about the address because we are going to use a special function register. Special function register for port A is known as port A, port B, port C, port D. So because we are going to use the name port A, which is a special function register, so you don't need to know the address. So that is indirectly solved. So you don't have to worry about addressing them or to know the address because you just need to know the port's name. So that is enough. So then there is the input-output synchronization. So the role of the interface chip is actually as shown here. It actually controls, synchronizes between the input-output device and also the microprocessor. For input, the CPU needs to make sure that it reads when the data is valid and reads only once. In other words, whenever there is an input information coming in, the interface chip will actually inform the CPU that the data is ready to be read. Then only it will read. So it will make all this arrangement first, then only it will read. I'm using layman's term. Don't go on technical like that. Whenever for output, the CPU needs to make sure that the output device is ready to accept new data. So the microprocessor will send a data here, but then the interface chip will check, is the output device ready to receive the data? So then it will send. If it's not ready, then if you send, you'll have data loss. Likewise, when the data have not even arrived and the CPU is reading, you won't read the proper input. You get the idea? So this is just the theoretical aspect of it. So the synchronization between the CPU and also the interface chip, there are two methods actually. One is polling and one is interrupt. Polling method is actually, what you will do is you constantly check. Polling method means, go back here. Polling method means the microprocessor asks, the data received ready here, data come ready here, data come ready here. Polling means repeatedly you will keep on checking. So you will keep asking, is data here, is data here, is data here, is data here. Say wait lah. Of course I won't say like that. Polling is actually like that. So it actually takes up CPU time in the sense that it keeps checking. I mean, if he's doing other work, he has to stop the other work and you have to check. Sudah sampai? Has it reached? So that takes up some CPU time. Then the second method is interrupt driven, which is on chapter 6, based on interrupt. One of the very important topics as well, and also interrupt is very, very widely used in a lot of hardware application and development. So interrupt means the CPU don't keep asking questions. The CPU will do its own job. Will do whatever it's supposed to do. When the data is ready, it will actually catch up. Interrupt means interrupt him lah, CPU boss. Data is here. Okay. You take and continue this work. So which one is better? Interrupt definitely is better. So we will see the usage of polling and also interrupt. And if you see in finals, usually they really want you to understand between the polling and also interrupt. So you should know how to differentiate between these two. So this one is key. So let's go and see now on the overview of the PIC agent input-output ports. So as I mentioned earlier, input-output pins are actually grouped into ports. So you don't need to know the address, you just need to know the port's name. A port usually consists up to 8 pins. Why do you think 8 pins? Why do you think 8 pins? Why 8 pins? Huh? It's an 8-pin processor, you should have 8 pins. Huh? You're transferring a data at time. Data here length is actually 8. We have data direction register, which is known as trace, and a latch register known as latch, and a data register is known as port. Remember, the input output is actually read from data register or sent to data register. For an input, the Input device is connected to data register, so the data is actually transferred to data register and the CPU reads from data register. To output, the CPU loads the value into data register and from data register it will be sent out to the output pins. So these are the ports. So in our application, we won't be using much of a latch register. We will be using data direction and also the port. So port means like this now I showed you. Can you see this? These are all port. This is RB means this is all port B. Port B, RB0 means is port B pin number 0. Pin number 1, 2, 3, 4, 5, 6, 7. So total how many pins? 8 pins. This is port B. Then you have port C. Pin number 0, 1, 2, 3, 4, 5, 6, 7. How many pins? 8 pins. Then you have port D. So 1 until 7, another 8. Because this one goes until port E, but port E only has 3 pins. And port A has 7 pins. Port A is usually used as an analog to digital converter. So most of the time, of course you can see each of this whole thing is known as port C. This is known as port D. This is port E, port B, and port A. So and each pin is connected to each pin. And if you see sometimes there's a slash right, that means that pin has more than one function. Any question up to this point? So these are the ports. So each pin you can configure as input or as output. So the data to be output is written into the latch, which in turn drives the output pin. So whatever we are dealing with, we always deal with the port. So whenever we send the data to the port will actually send the same data to the latch register. The latch register is actually connected to the pin circuitry. So that's why it says that the latch drives the output pin. So from the data port, you only write to the data port. From the data port, it actually will transfer to the latch register. The latch register is actually connected to the pins, the hardware pins, circuitry, and which will provide the correct logic to that particular pin. So PIC 18 may have as many as 10 info output ports. That depends on how many number of pins that we have. Just now I showed you PIC 18 is actually 40 pins. So if you have more pins, you have more ports. And info output port is often multiplexed with one or more peripheral functions. I just mentioned that one pin there's a slash right. So it means you can also use that pin as input output or any other functions. But you can only use one function at one time. You cannot use as both. Devices with 18 pins, okay, these are the 18 pins. ICs have 2 info output port because of the limitation of the legs. They have lesser port. So 28 will have 3 ports, 40 pins, just now I showed you. DIP package is dual input package, which means it has the leg. 44 pins PLCC package is actually surface mounting, it's flat. It's actually soldered on top. So they have more ports, A, B, C, D, and E. Devices with 64 pins, 44 pins is actually also, but it's a bit different package. This is actually the SMT one. So you have 64 and 68, they have more pins. That means the number of legs is actually even more. So most 80 pins have 9 ports, depending on your microcontroller. Basically you can have as many ports as the leg number increases up to. So these are, as I mentioned earlier, port A have 7 pins. Usually it's used for analog to digital converter. The rest will have 8 depending. Like just now I showed you the E, we still have E but only has 3. So it may vary depending on the microcontroller model. Now the next part is how do we actually read and write the input-output port. So the first thing is data direction needs to be set before the input-output operation. To configure, here for this example, I'm focusing on port B. So RB is referring to port B, and this one indicates the pin number. All this indicates the. Now, as I mentioned, all these pins we have the pins right. They have the output pins, sorry, input-output pins. Now this input-output pins you can configure whether to become input or to become output. So let's say this pin number 1 we want to connect to a switch. Typically how we actually connect a switch. Why we want to do like this? Can we connect a switch like this? Can we actually connect the switch like this? Why not? No pin. No? No what?
No output.
No output port. No, this pin is actually input. No, don't worry. I assume there's something here. You have to look for the tiniest mistake. Assume it's connected to a pin. And we want it to become input pin. We are focusing on the input now. Okay? I mean this switch means input. How can switch be output? Switch has to be input. My question is, this configuration of switch, is it can we use it? That's my question. Why cannot? Because of the ground. What ground got to do with this?
There's no output. Where's your light? Where's your LED?
Come again?
Where's the LED?
Where is the LED? We're talking about input LED. LED, wait first. Just this input part,
This is
we're focusing on the input part. My question is, can this configuration can be used as the input switch or not?
Yes.
Now, see, not telling it. It's not telling no. So why you all tell no first? Huh? No sir, because you draw something, then you draw the second one, sure the second one got some problem. Today we cannot use this one. Yes. Why? Why cannot use this one? What's wrong with it?
5 volt resistor switch.
Should have known
Signal.
this. What's wrong with it? No negative. Logic 0 don't have negative. Why must have ground? Okay, if I press the switch, the circuit is complete. Assuming that the microcontroller, okay, take note that the microcontroller has a positive voltage and also a negative ground. Of course, I'm not showing in the diagram here, but take note that like normal any other ICs that you have used in your digital logic lab, you connect to the power source, right, and also grounding. Likewise, this one also have the grounding. So if it's ground, assuming that this is already grounded, so if I press the switch, it's complete circuit. So yes, it can work. So why cannot?
Can, but why?
Okay, I save your time now. When you press the switch, what's the logic at this pin? When I press the switch, 1. When I don't press, what's the logic?
0.
Why? How you know 0?
Because there's no input. It
How you
stops
know 0 when
connection.
I'm not pressing? How you know it's 0?
It stops
It's
connection.
floating. It's not 0. Yes. Is it connected anywhere? No, it's floating. That's why we cannot use this configuration. When you're pressing, yes, it's logic 1. Take note that this is hardware. Digital hardware needs to know 1 or 0. When you're not pressing, this is floating. Floating is not recognized. That's why you cannot use. Therefore, you need to create a configuration where it either gives logic 1 or logic 0. So that's why we have this kind of configuration. So when the switch is not pressed, what is the logic at this pin?
1.
When the switch is pressed, what is the logic at this pin?
0.
0, because we are shorted to ground. You understand? Yes or yes?
No. Off.
Not giving you option anymore. You understand? Yes or no?
Off.
Okay. So this is the input part. Okay, now we have connected one input switch. As I mentioned earlier, each one of these pins, you can configure it to become input or output. Okay. Whenever we want to write or read, we will be dealing with the data register. In this case, this is the port. Which port we are dealing with?
Port B.
Port B. So the data register name is port B. Now port B has 8 bits. Each one of these bits represents the pin. So pin number 0 is actually RB0. You are following? Likewise, pin number 7 is actually RB7. Is it okay? So now, out of all these pin, which pin that you want to configure? Pin number 0, right? You want to make it as input or output? Input. So we want to make pin number 0 as input. So for that, you need to configure. So where do you do the configuration? you do at 3B. Now each port has its own 3's register. That means port A, 3A, port B, 3B, port C, 3C, port D, 3D. Is it good to understand? Each port got its own data register, data direction register. You understand? So here is where we do the configuration of input and output. So at the 3B, if you write the value 1, you configure it as input. If you write value 0, you are configuring as output. So bit number 0 in 3B, I need to write the value 1 or 0. I should write the value 1 here. When I write the value 1 at 3B position number 0, it actually configures port B's pin number 0 to become input. Do you understand?
No.
We have this data direction registers, we have data registers. Whatever data that we are going to read or write, we will be dealing with data registers. You can understand?
Yes.
But these data registers need to be configured as input or output. The configuration of input and output is done at the data direction register, known as the 3's register. Each port has its own 3's register. Since we are dealing with port B, so we need to configure at 3B. Now the setting is, if you write the value 1 in the 3's register in that particular position, it means that that particular position in that data register will become either input or output. So this is quite easy to remember that. 1 represents like I, so you know the input. 0 represents like O, so you know the output. So whatever configuration value that you write here will determine the pin direction of the data register. So since now I want the pin number 0 to become input, so I am writing here 1. The rest how?
0.
The rest actually I don't care. Doesn't matter. So I can just put 0, 0. So that means what am I configuring port B to become? Output. Only port B pin number 0 is input, the rest all I am configuring as output. Of course, if you want, you just put all 1. If you put all 1, all the pins will become input. Do you have any question? This is quite the most simplest thing. For input, you are not going to write anything. For input, you have to receive the input from here. So let's say you did this kind of configuration. When you are not pressing, the value in port B will be 1. When you press, the value will become
0.
You understand? Any question with this one? Let's say now we want to connect an output in the LED. In order for me to turn on this LED, what is the logic that I should supply here?
1.
Logic?
1.
Zero,
Logic
right?
should be. What is 0?
Why I feel like killing you?
Should be
Should
1.
logic 1 lah. Why logic 0? It's already connected to cathode, right? You need a forward bias. Put logic 1 lah, then only you can see the anode, cathode. So you need to supply logic 1 to turn on. Okay, that's a different story. Now we have made this configuration at port B pin number 6. So which means this pin number 6 is supposed to be output, right? Because here we already configured it to become output, so it's okay. Fine, so it will work. Take note that if you configure the pin wrongly, for For example, pin number 0 is supposed to be input, but you configure its output, you will never get the value because it controls the data direction. When you make it input, the data direction moves like this from outside to inside. When you make it output, the data direction goes like this. You understand? Understand or don't understand?
Understand.
So this is a simple principle of configuring ports. Like peanuts, right? Yeah, good. Okay. So easy. It's very easy. So let's see how do we actually write the coding for this. For this one. Sounds okay, right? Actually, we are only concerned for this one and this one. The rest is actually don't care. So as long as this one is 0 and this one is 1, the rest whether it's 1 or 0 doesn't make any difference. Because the rest is not connected anyway. Not connected anyway. So how do you actually configure like this in terms of coding? Or configure this one? You actually use all these ports you treat like a normal file register. Just treat like a normal file register. Nothing great about it. So what is this in hex?
1.
Can you just
Move
it to
choose B. W. Choose B successor.
so this is perform the configuration. Is that a good thing? Is it okay? Okay, now we're dealing with two ports, port B and also port C. Just erase this part. So in port B we have one input. In port C we have after the dot means the LED is connected to all the pins. Then we have 8 LEDs. So since now you have 2 ports, anything, just remember in the input output for the first thing that you do is configure. So for port B, you want to configure it as input or output?
Input.
Output. Port B. So what should we do to this B?
FF.
So because we're just dealing the one, I can also configure just that one bit. So I can use bit. This one I need to bit set F to this B pin number 0. Pin number 0. So I'm configuring port B pin number 0 as input. And then the port C I need to configure as input output. Output. So what should I configure at 3C? So I can just use clear F. Clear F has how many feet? So when I use clear F 3C, In 3C, all the thing becomes 0. In other words, it configures all the pins in port C to become output, not become 0. Take note that whatever you write here, don't think that then here also will be 1. No. This is just configuring this one. Is that clear? Always students have this confusion. Whenever we clear F3C, port C also will have all 0. No. When you put clear F3C, it is only configuring the port C to become output. That's all. Is it clear? So this is the configuration part.
So repeat the QF.
When you clear F3C, all the position inside 3C will become 0, right? What it indicates is every single bit in port C is output. Is it okay? So if you substitute this with C, you write all 0. What it means is that every single pin in port C is configured as output. That doesn't mean that a port C is 0. It just means that all the pins in port C is output. That's all it means. Is it okay? Can I move to the next one?
Sure.
After you have configured, just remember this, whenever it comes to port, the first thing is always configure. Configure means trace register. So depending on which port, you configure those trace register. As simple as that. Is it okay? Now the next thing is you need to do initialization of the ports. Now where do you do the initialization? You only do initialization to the output port. For example, here LED, right? You may want to initialize it so that it is off initially. If you don't do it, sometimes you can see the LED tend to blink here and there. You want to forcefully initialize it to 0. Now that depends on the question. Sometimes the question requires you to initialize it to 1, which means they want the LEDs to be on first. But in this case, let's say we want to initialize it to become off. So what should we write to off port C? That depends on the configuration of the LED, right? In order for me to off the LED, what is the logic that I should provide as a pin?
0.
0. Can this be used? Can this configuration of LED be used? No, sir. And yes, it is the reverse way of doing. Actually, this one is more popular than that. This is actually you are supplying 5 volt to the LED, and this pin must be 0 in order for the LED to turn on. So this allows the current sink in. Now this one is better than this one because this one, the power comes from the microcontroller. It is supplying the current. It's actually more energy consuming or power consuming because it is giving the output. Whereas this one, it is actually allowing the current to sink in. That means the current source is coming from elsewhere, coming in, going here and going down to the ground. So this is actually known as a sink-in current. So microcontroller PIC18 has a very large tolerance for sink-in current. I mean it can actually allow large current to flow through it, but it cannot supply a large current. The current that comes out here is only like milliampere, very small. I think less than milliampere. See the data sheet. But this is much more better. When you do this, is the microcontroller using any energy? No. It is just allowing to pass through, go to ground. If you want to come up with a design which is more energy saving, you should do something like this. And most of the hardware boards, all they have like this, not like this. Exam always come like this. children get sweating. So why wrong? Schematic is wrong. The schematic is correct only. Sir, no, it is wrong. So there's two ways of interfacing. You okay? Now coming back, this one, in order for you to turn on LED, you need to supply logic. We want to initialize it, right? We want to initialize it. We want initially all these LEDs to be off. So we must supply logic 0. So what is the value that we should write to port C?
0.
0. So how can we do that? Yes. Okay. Clear at port C. Therefore, all the writing and also reading should be done at the data register. Configuration is done at the trace register. Is it clear? So when you do this, clear at port C, initially all the LEDs will be off. The next thing is, we have a switch here, right? Let's say when we press the switch, we want all the LEDs to be on. So how can we actually check whether the switch is being pressed or not? That is, if you see in your instruction set under the bit-oriented instruction, first page, there is one instruction known as bit test file register. Bit test is actually bit test. It's actually testing the bit. There's two bit test instruction. One is bit test file register skip if set. One is skip if clear. So in either way, you need to use the bit test because it checks. It checks the port P. Just now, Theban asked that, how do you know what value to write here? For input, we don't write the value. We check the value. So in order for you to check, we need to use bit test. So we use bit test to check this particular bit. What are we checking for? Bit number 1 or bit 0?
0.
Bit 0. Because remember, this configuration, when you press the switch, it gives you logic 0, not 1. When you're not pressing, it's giving logic 1. So this is the initialization part. So you have that bit test file register. I'm going to use skip if set. So where are you testing the bit? At which port?
B.
Port B.
Port B.
Or pin number
0.
0. You are testing this pin. So what you're testing for? Skip if set. Skip if set means what? Is the button being pressed or not pressed?
Not pressed. Not pressed.
If the pin number 0, if it's giving logic 1, is the switch pressed or not pressed?
Not pressed.
Not pressed, right. So it will skip if set, which comes here. If the switch is not pressed, what you should do? You should keep checking. Huh? So skip will come here. So you should go launch, check. Why should the check go?
BTFS.
Here. You should constantly check. Do you get the idea? That's why it says skip if set. Set means what? The switch is not pressed. Because when you're not pressing, the logic here is 1. 1 is actually set. You all know that term, right? Don't know. Okay, set means 1. Clear means 0. Hope that clears the doubt. Is it okay? So now you understand this one? Skip if set means, how come you don't know? Digital logic you have done set. What do you use the term for making it 1? Tell me now. What do you all use the terms? Off the camera for what?
Transfer.
Hey, before transfer is still learn.
How many years ago?
Okay, what do you call in digital logic when you want to convert the logic 0 to logic 1?
Reset.
That's set, right? You set. Okay, never mind. Past is past. I think you all erase it using the ink from UV light. So now just to recap back, set is 1. Clear means logic 0. Is it okay? So because we are using this configuration, why we are using this configuration? Because this configuration gives us 2 logic, 1 or 0. So when you're not pressing the switch, the logic is 1, which means the button is not pressed. So skip, it will skip, it will come here. So we need to constantly keep checking. Now if the button is pressed, what happens to logic? It becomes 0. So will it skip?
No.
No. So at this part is where you can write the instruction to manipulate these LEDs. So let's say we want all the LEDs to turn on. So what can you write here?
MOV.
I want all the LEDs to turn on. What should I write here?
DSM.
CSM. Set F lah.
Set.
That is set F or
C.
Port C.
set F also have 2 fields. 2 or 3.
2.
Like I'm trusting all. Is it clear? So that means the flow of the program is